So we're going to talk about the introduction to electricity tonight. So how many of y'all remember what an atom is? ATOM, not ADAM. I know they sound very similar. All right, so yeah, some of y'all still remember a little bit. So we're going to talk about a little bit about the history of electricity, the language of it, the structure of matter, the structure of atoms, the structure of electron shells, which is the part we actually use of an atom, how we transfer charge, electrical forces, electrical terms, and electrical safety. Now, I will go ahead and tell y'all now, I'm a safety nut. And there is a reason for that. We'll get into that as we go. All right, so history of electricity. Now, they say it was discovered in the mid-1800s. I tend to think of it as it was rediscovered. The reason I say that, they have a lot of interesting archaeological finds out there in the world. One of them is a jar, a ceramic jar, that was filled with an electrolytic material. So this is something that is able to conduct and move electricity. Now this was found at an ancient, I can't remember, I think it was a Babylonian site. So we're talking ancient history, like prehistory. Okay? And the material and the metals that this whole thing was comprised of created a battery. A honest to God battery. Didn't have a lot of voltage, but it was an honest to God battery. So we tend to think it all started with Ben Franklin and his kite and his key, which, by the way, if that was an actually true story, that would be kind of psychotic. Because think about it, the whole story is his son is running around outside with a kite in a lightning storm. Think about that for a minute. Just kind of think about that. What would that be today? Can you say child endangerment? So you really can't tell me that electricity was discovered in the 1800s, because if you really start investigating, we've always known something about electricity for a very long time. So the biggest thing is that electricity and magnetism are very closely related. We'll get into more of that as we go. The biggest thing is we have what's called current. This is the flow of electrons in a material. As electrons flow, they create their own magnetic field. Okay? And this electromagnetism relationship is pretty much the basis of all society today. We're going to talk about a couple of really interesting characters as we get into this. Okay? All right, so we have what's called voltage, or if you work with military, they call it an electromotive force. Okay? Either one's wrong, because you will see that in a lot of textbooks and a lot of anything to do with military, instead of voltage being labeled as V, they label it as E. E stands for electromotive force. You might want to write that in your notes because you can get confused with these two. A lot of people don't recognize when they're given E that it is the same as V. Voltage has become more of a shorthand term. Does that make any sense? Because voltage is the unit we use to measure we have taken to using that instead of using E, because who wants to say electromotive force over and over again and pray you don't get it wrong? You know? I don't know about y'all. Eventually I get tongue-tied and everything kind of ends up not sounding correctly. So the second thing is that current is electricity in motion, and you will hear the term current quite a bit. All right? You have static electricity, and this is electricity is at rest. So this is electricity that is not moving. And we have, well, most of you have heard, probably remember static electricity from elementary school. How many of y'all remember the balloon in the hair thing? Or rubbing your feet along the shag carpet so you can go zap somebody? Yeah, all of us have done that, right? It's so much fun if you have a sibling or an unsuspecting relative. You sit there and go, ha 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 ha, zap. We have fun doing that as kids, right? Why is it fun? Because the reaction is funny sometimes. Whenever you see somebody jump out of their skin because they didn't realize you were behind them when you zap them. But static electricity has its drawbacks too. We're going to talk a little bit about that as we go. So the structure of matter is the building blocks of everything, including electricity. If you remember from physical science class, or I think middle school science, you learned that atoms are composed of three things: protons, neutrons, and electrons, yeah? Where are protons and neutrons located? Where are protons and neutrons located? They're located in the center. They're the core of an atom. Okay? So the only way to really separate protons or neutrons from an atom is to use an atom splitter, which that kind of equipment is generally very expensive, can create nuclear or toxic waste, and is not something that you really do on a daily basis. So if protons and neutrons can't be used, what do you think are? Electrons. So all matter is said to be electrical because all matter has electrons. And this is true. Even the things that we think cannot conduct electricity, it can. We'll talk some more about that as we go. All right, so matter is anything that has mass and occupies space. Do you think that means air? Is air made of matter? Yes, yes it is. So molecules are the smallest particle of an atom that retain the properties of the atom. Okay? Now, I'm kind of passing over some of this because a lot of it gets a little bit deeper than we really need to go. Okay? Matter is made up of atoms. And matter is anything is that the atoms have the correct properties of themselves. It's the easiest way to say that. So when all of the atoms in the matter are the same kind of an element, okay, we have more than 100 elements, 92 that occur in nature and are stable. What are the rest? If 92 are stable, the rest are unstable, probably nuclear, right? So they only exist momentarily during a nuclear reaction of some sort. Now, that's not to say that they really change what they are. It just means that, how to say this? So nuclear material does not technically change what it is. Cobalt, I think it's cobalt 62. All you're really changing about it is how long it takes to break down. So it's still cobalt. It's just breaking down of the atoms themselves. The atoms themselves are so loosely bound together that they just keep breaking apart. I guess is the best way I can explain that. Excuse me. So the atom is the smallest particle of an element that retains the characteristics. You have protons, neutrons, and electrons. Of course, you probably remember protons are positively charged, neutrons have no charge, and electrons are negatively charged. This is all very familiar, right? You should have had this in middle school science as well as physical science when you got to high school. So protons and neutrons are located in the nucleus and the electrons are located outside. Okay? So we use the electrons because they are not bound to the inside of that atom. They hang out on the outside. Okay? Does that make sense? So electrons closest to the nucleus have less energy. They like to stick together. The electrons orbit in what are called energy shells. Much like the planets in our solar system, they hang out on the outside of the atom. Okay, protons and neutrons are the sun. Can we get rid of the sun? You think we can do anything with the sun? Nope. Now, do planets occasionally get lost from our sun? Yeah, that's kind of how Pluto happened. So electrons orbit in energy shells. Okay. The last or outermost shell is what is called the valence shell, and that's the stuff we use. And the ones that are located there are valence electrons. The number of electrons, if your electrons and your protons and your neutrons are all the same, you have a neutral atom. What does that mean to us? It means that, we need a different kind of charge to change the state, right? We're going to have some form of something to change the state of it. Okay? Because honestly, atoms don't want to be charged. They want to be neutral. They just want to be left alone. Okay? So each shell has a maximum number of electrons they can contain. So the first shell can only ever contain 2. The second shell contains up to 8 electrons, and so on and so forth. Okay? The truth of the matter and the base of the matter is that electrons in the outermost shell, you will only ever see 8 per shell. That is a maximum of 8. How many of you remember the saying, if it has 8 electrons, it's a happy atom? Y'all remember the happy atom thing? Not really? Dang. I cannot tell you how many times my science teacher repeated that over and over again until I'm just going, I don't care about a happy atom if you say that again. I'm going to start looking for something to throw just to get out of class. Yeah, for some reason they liked repeating that over and over again. 8 electrons make a happy atom. What that means is that all atoms want to have 8 electrons in that outermost shell. The only ones that are different about that are, I believe, the first two, which are hydrogen and helium. They only have the single innermost valence shell, which should only have 2 electrons. So hydrogen likes to bond. It likes to bond a lot. Helium doesn't like to bond at all. It's full. It doesn't like to bond. It says, nope, don't want to have anything to do with you. Bye. And that's helium. Hydrogen always likes to go up to the nearest person and say, hey, bud, can I borrow your electrons? Can I be part of you? Which is why it bonds so easily. That's why we have H2O. Okay? So the outermost shell, if you're dealing with hydrogen, 2 electrons are required. Everything else requires 8. Okay? Good rule of thumb of that. So each element has an atomic number. This is the number of protons in the nucleus. Now get that we're saying protons. Why do we specifically want to count protons? It only equals the electrons if the atom is what?
I know the word. It's not an ion. No. No, there's like a copy of the element.
If your electrons equal your protons, you're electrically neutral. However, we just talked about the fact that electrons don't stick very close to their atom, right? So what that means is that electrons can go away or they can be gathered up. So instead of trying to count by electrons, we count by protons and thereby count by neutrons. Okay? Because protons don't leave the atom unless you got an atom splitter somewhere, which those are kind of rare to find in the world, mainly because they take a lot of energy to use. You split an atom, it takes a lot of energy to do so. Okay? So positive charges cancel out negative charges, and your atom should be net zero if its state has not changed. Okay? Most atoms like to start out in neutral state. So we have 3 categories of materials. We have conductors, which these are the things that conduct really well. You have semiconductors, which kind of sort of conduct pretty okay. And then you have insulators that they don't like to conduct at all. They like to hold on to their electrons and say, nope, no way, you ain't taking these. Nope, you're not going to grab these. Okay? This particular page is something you might want to write down in your notes, guys, because this is good information right here. Because I can guarantee you there will be test questions on this. So conductors have 1 to 3 electrons in that outermost shell. Those electrons in that true outermost shell are very loosely bound to that particular atom. In other words, they like to go away and come back. They're very, very loose about how well they hold on to it. Semiconductors have 4. And then you have insulators, which have 5 to 8. Insulators don't like giving up their electrons. For those of you that do have your book, if you look at page 93, you see just about a periodic table of elements.
And I wanted to crawl space a lot of times. I would fly around and stuff.
Page 93, yes. Table 6-1, which is electron distribution in atoms. Okay. And I'm not so much interested in some of these as I am in others. Where it says something is an inert element, INERT, what that means is that element is non-reactive. It means that that particular atom is very happy on its own. He does not react. Put to you this way. You ever tried to fire off helium? It doesn't like to fire off. It's not very active to fire to anything, right? It's fairly stable. Versus hydrogen, which there's a reason there's called the hydrogen bomb. Okay? It's a very active element. It likes to move. You have, if you look at this, things like sodium and magnesium. These are very active elements. You have aluminum, which where do we use aluminum a lot? What do y'all think? Coils where? Yes. But we use it. There's something even bigger. Something that we use countrywide and even internationally. Even bigger. The biggest use of aluminum are power lines. The transmission lines, the really big lines, those are all aluminum. Now, why would we want to use aluminum over any other element? What y'all think? It's cheaper. It's conductive. What else? Flexibility. What about weight? One thing of copper versus the same of aluminum. Aluminum weighs a lot less. That's the reason we like to use it for transmission lines, because if you're going to set this up, you don't want your lines drooping a lot because of their own weight, first of all. Second, you don't want somebody overly tempted to climb a line and take it down. Yeah? I mean, well, truthfully, you would not believe some of the stories I've heard. Because I've met several guys that work for the county and are working for the county electricians that keep the street lights on. Would you believe how many times somebody will break into a street light and strip it? Yeah. You're dealing with a minimum of 120 volts and quite a bit of current going through those lamps. And yet people will strip out the internals of it in a heartbeat. There are people that have been killed doing so because they get across that electricity the wrong way and they get zapped. You would not believe the stories I've heard. My dad worked for Alabama Power for over 30 years. Most of my life. You wouldn't believe how many idiots crawl into substations to break into the bunkers they have there to steal any copper wire they have. Think about any time somebody breaks into abandoned houses. Or you have foreclosures. What is the biggest issue with foreclosures? Buying a foreclosure, huh? It gets stripped out quite frequently. A lot of foreclosures, it's not the people out there, it's the actual owners that will strip it. And they will pick that carcass clean. They'll take every last bit of pipe, and they will take every last bit of wire that they possibly can get a hold of, and they will go sell it. So that's one of the biggest reasons we use a lot of aluminum. And that is one of the biggest uses of aluminum. Because think about how many transmission lines there are just across the US. Yeah, it's a lot of aluminum, right? Occasionally you do have to replace those lines. But aluminum, if I'm right, I think it has 3 in that outermost shell. So it's not a great conductor. It's not copper. It's not gold, which gold, silver, and platinum, 3 biggest that conduct most easily. Honest to God truth. That's why what's in a lot of computers? A lot of the traces in computers are gold. But the thing is, there's so little gold that you'd never make any money getting it out. Yes. So the way that they make those, a lot of them are made with gold or silver. And sometimes even platinum.
They change the color, don't they?
No. If you look at these boards from the side, this is kind of what they look like. They're multi-layered. And the tracings of these are less than the width of a human hair. So there's not a lot of gold in it, but the gold could very well be this layer or any one of these layers. It's just not worth getting it out. Surely it's not. It would take more energy, more time, and create more waste to get the gold out of a circuit board than it would be to just go buy gold. Honestly, it really is. It's amazing what some people will do, though. But the traces of the gold are literally less than your fingernail. So look at your fingernail. Look at how thin that fingernail is. It's less than that. It's barely there. There's a reason I'm telling y'all this. But before we get to that, what would each of these be classified as? So what is this guy? Knowing what we know, insulators have between how many? 5 to 8, right? 5 to 8 in that outermost shell. So we're looking at this shell right here. Semiconductors should have 4, and conductors should have between 1 and 3. So what's this guy right here? He's a conductor. This guy over here would be a insulator, and this would be your semiconductor. Now, semiconductor still conducts. All of these can be told to conduct something. What's one of the biggest known insulators? Rubber. Does rubber conduct? Rubber conducts. And the coolest example I've ever seen of this, who knows what an electric eel is? Mhm. This is a fish in the Amazon that can swim right next to its prey. This thing has almost no eyes. The eyes are smaller than any animal you should have a right to have. So in order to catch its prey, it swims up next to its prey and it's able to release electricity from its muscles and it's able to zap its prey so it can eat it. Bioelectricity. Very cool. Now, if you ever watch fishing shows, there's a couple of them that have handled these fish. And there's one that he got a little water in his gloves, in his rubber gloves. And you would think that wouldn't matter because, hey, he didn't have the fish in his gloves. He was just picking the fish up out of the water. Except that the energy from the fish was transferring through the rubber gloves thanks to that water. It was throwing off enough electricity that he was feeling it even with the rubber gloves. Okay? So yes, rubber does conduct. There are conditions under which you can make anything conduct. It's just a question of how much voltage and how much current are you willing to put through it to make it conduct. Okay? So we have what's called ionization. Since we can move those electrons, when we do so, it's called ionization. Okay? So if an atom loses an electron, so let's think of electrons as that very negative person in your life. We all have a few of them, right? So if you lose one of those friends that's negative and dragging you down, you become a more what? You become more positive as a person, right? Think about that. However, if you're the person that ends up gaining that friend, you tend to become more negative. Same thing for ions, okay? If you lose an electron, if you're the atom that loses the electron, you become positive, okay? If you're the atom that gained the electron, you become negative, okay? Does that make sense? I had somebody tell me that example and I just always used it ever after. It's a good idea. It's a good visual, you know? Because we all have something negative in our lives that if we lose it, we become the positive person. And we also have the ability to gain that negative person and then we become negative, right? Kind of how life goes. So copper is one of the most commonly used in electrical circuits. It only has 29 electrons with one valence electron. Now, copper is frequently used. However, aluminum is used just as much. In fact, you can actually find houses that are wired completely in aluminum. There's nothing wrong with aluminum wiring. It works just as well as copper. Cost and perception. Most people don't think to use aluminum wire because copper has always been the traditional thing to use. Not to mention what you have to do when you're dealing with aluminum and copper because they both expand and contract at differing rates whenever exposed to heat. So the bad thing about aluminum to copper, if you don't make that connection really strongly, then they can actually untwist themselves and come loose. So It's one of those things of either you wire it completely in aluminum or you wire it completely in copper. If you try and start mixing them, you've got to be real careful about it. Just because if you don't have that solid connection, you can really be looking at trouble. Does that make sense? Copper is the better conductor, but you are dealing with the fact that it is more expensive. Somebody tell me exactly what copper costs right now. Yep. So what is the value of copper currently? Anybody know? Let's see. Copper price per pound is $4.34. So not bad. Not terrible. But it's not cheap either. Yep. That's per pound. So, yeah. Since most piping is done in PVC these days, or anything else, it's a lot cheaper than it used to be. These days, we don't use a lot of copper pipes unless it's for very specific use. Hmm? There are certain things we still use a lot of copper for, but copper's becoming since it is becoming more expensive and it has become more expensive over time, it's becoming less used because you can get PVC, you can get all sorts of other things for cheaper as far as piping goes. Electricity, you can use aluminum, just depending upon who you go to and what electrician they are. There's all sorts of other options. Copper is the most commonly used because it is just a traditional thing that's been used. Hmm? Well, I mean, ever since the discovery of well, I won't say discovery, the so-called discovery, and I use that very loosely, ever since the major revolution of electricity, that's a good way to call that, the revolution of electricity. So ever since that really came about, copper's been the big thing. Because copper is very abundant. You know, it's far more abundant than gold or silver, which conduct far better, um, and are far easier to use. But gold, very expensive. Why? Because it's very rare. Same for silver. Though silver's not as rare as gold, it's a little more rare than copper. Copper's easy to find. We've found it for millions of years now, or thousands of years rather. So there is that. So, yeah. So copper is one of the main things we use. So as far as electrical forces, all right, it is all to do with the protons and electrons. And that is because, just like with magnets, which I wish I had some magnets up here. So just like with magnets, what happens when I put two like charges together with magnets? They push away, right? They don't want to go together. One always wants to flip to the other side. Why? Because likes repel, unlikes attract, right? So this is the very basics of how electricity works. Like charges repel. Differing charges attract. So, and of course, uncharged has no force. It just kind of sits there. One of the biggest things we measure electrical charge in is what's called coulomb. And 1 coulomb is 6.25 times 10 to the 18 electrons. And yes, that is an actually very good thing to write down or to highlight in your notes. So 1 coulomb is 6.25 times 10 to the 18 electrons. Okay. As far as history goes, we have two forces of electricity that we study. One is called DC, or direct current. That's going to be the next bit that we start talking about. Now, who is credited with being the father of DC? Does anybody know? And I use credited because this guy was, I'll say he was clever. Because he had a nice little think tank going, and he patented everybody else's inventions under his name. That would be Thomas Edison. He is credited with being the father of direct current. So if we have DC for one, the other one is what's called alternating current, AC. And the father of that particular branch is a very brilliant, if kind of crazy dude. Anybody know his name? Not Einstein. He was way after these guys. Huh? It is Nikola. No, it's not Nikola. It's Nikola. Nicholas. It's Nikola. Nikola Tesla. His name's not spelled like Nicholas, but I think it has the same intention as Nicholas. Tesla goes back. He's actually, the story between him and Edison, and the reason of the rivalry is that Tesla initially went to work for Edison in his think tank. And Tesla was extremely brilliant. In fact, everything in our modern age, Tesla built the prototypes for it, and he dreamt it up long before it ever came to pass. He created the first RC boat. Yeah, he created the first radio-controlled boat. And he would take it out, and he actually showed it off. Really cool. Well, heck, I never heard the name Nikola Tesla whenever I was in school. It was all Edison. Yeah, but the thing is, Tesla, he created our modern age. He dreamt of everything we are trying to put in place today. Extremely smart. Look him up. He is the coolest guy out there. So he is the father of AC. He and Edison got into it. Edison said that his inventions should never work. As a matter of fact, Edison tried valiantly to tear Tesla down a lot. Tesla was very interesting. He was actually funded by J.P. Morgan. Up until J.P. Morgan backed away from Tesla, saying, "Oh, we don't have any money anymore. We're just not going to fund you anymore." And Tesla was broke. Let's just say, if you ever get a chance, look him up. The craziest thing he ever did was he used to claim he could talk to aliens through his radio. Kind of crazy. But Yeah, if you say that you talk to aliens even today, you're not considered sane. Huh? But as far as the history of electricity goes, those two guys are the ones that really kind of kicked everything off and really kind of got electricity going as the major thing worldwide. Um, the thing is, we don't really use a lot of direct current anymore. And that's because it's not as efficient as in transmission as AC is. Yes, in circuit boards and things like that, we use direct current because it's safer. It's a steady state voltage. Right. There it is. All circuit boards use DC, and there's a reason for that. AC is every bit as dangerous as Edison used to tell people. AC is one of those things. Edison was actually the one, by the way, that built the electric chair. Um, Again, very interesting story. Read all about it. It is very, very interesting between the two men. So, DC is a steady state voltage that does not change over time unless you force it to change. On the other hand, AC is alternating current. AC is not steady state. Matter of fact, what are you supposed to have on all your electronics at home? Not a fuse, not a transformer. Surge protector. Y'all all know what a surge protector does, right? If your electronics start to pull too much energy, if it starts to pull too much current, that surge protector trips and it saves your electronics. Okay? The surge protector is supposed to trip and save your electronics. Okay? So when it comes to transmission of power to large sets of everything, we like to use AC because we can push it anywhere we want to. And it does not take as much effort to move AC. DC, on the other hand, kind of peters out over time. It just does not have the strength to go the distance unless you have to continually step it up. However, DC is good because it does not spike. What do I mean by that? I mean that if you look at a signal for AC, you will see occasional overspikes. Okay? This means that while you're supposed to have 120, you could end up with 500 volts at any one time. That 120 is just an average. That can be very damaging to electronics if you do not have a surge protector. So in order to protect electronics, we put surge protectors in place. We have AC to DC converters that are supposed to save your computer if it does this. And we have everything running on DC to protect it. Okay? It doesn't take much to fry out electronics, and there's a reason for that. And it goes back to the fact that electronics are all made of nothing but essentially plastic and little traces of gold, silver, and other precious metals. If you put too much heat onto any one of those items, it will melt it. It makes it completely useless. And that is the honest to God truth, guys. So that's why we prefer to use DC instead of AC when it comes to delicate equipment. It just saves it. It saves it quite frequently from total disaster. So electrical terms, we have electric current. We have what's known as a circuit. Potential difference, we'll talk about. Resistance, and the difference between what is known as a cell versus a battery. And yes, there is a difference. I think I've got one with me somewhere. Or I did at one point. I'll have to find it in a little bit. Give y'all a break. There is a difference between a cell and a battery. So electric current, this is when electrons flow. Current means electrons flow. Now there's a reason I'm saying that. Because there's often questions on the test that say it makes protons flow. Do protons flow? No. Not unless you've got some sort of atom buster to force the protons away from the neutrons. It is not going to happen. The only thing that moves in an atom are electrons. They like to move a lot. They like to move very frequently. Okay? So it is literally electricity in motion, and the way we tend to think of it and its motion is what we call positive flow or conventional flow. The way it actually moves is, since we're dealing with electrons, we're not flowing from positive to negative. Now, guess what? It flows from negative to positive. Flows the other way. Does that make sense? We tend to think of it as positive to negative. It really is negative to positive. Why? Because we're moving electrons. They like to move. All right. So there are three things that make up a circuit. You have a voltage source, you have a load or something that does work, and you have to have a path for current. So let me put it to you this way. How many of you drive just for the sake of driving? What, nobody?
Right here, right here.
Most people do not drive just for the sake of the drive. You have a destination in mind, yes? Generally, you're going to the store, you're going to go to a sporting event, you're going to go to work, you're going to go do something, right?
Does clearing your head count?
I really couldn't say. So one of the things you have to take into account with this is that your source is your house, yes? That is where you originate from, is your house. In order to get from point A, your house, to point B, let's say you're going to the store, to get from point A to point B, you have to have what? You have to have some form of a road, right? That would be your path. You can't exactly go driving over people's houses and their yards. You have to have a road to drive on so you can get from point A to point B. Source, path, and then you have to have some place where you're going to do something. I don't care if it's chill with your friends. I don't care if it's you're going to go to work and actually build something, or if you're going to be going to the store to buy something. You have something in mind you're going to do at the end of the road. And then you have to have some place, you have to have roads to get you somehow back to where you belong, right? Which is back to your house. Same thing for electric circuits. You have to have a source, You have to have a path and you have to have a load. You have to have some reason for the electricity to work. All right? Does that make sense? So an electrical circuit can be represented in a schematic, which is a graphical representation of a circuit using standardized symbols. Why do we use standardized symbols, do you think? Because we want somebody from any other part of the world to be able to come over and be able to understand the circuit that we have in front of them. Symbols are standardized just about worldwide now. Now, that doesn't mean that the voltages and other things are standardized. I think in Europe their voltage tends to run 130, 150 or something. They run a higher voltage than we do. We run it at 120. They run it a little bit tougher. But they should still be able to come over and use anything we do. So you have the picture representation. So this would be, some kid, very basic circuit. You have a battery, you have wires, and you have a light bulb. The battery powers the light bulb, right? The better way to draw it and the simplest way to draw it, and a way that everybody that has known electricity would understand it, is drawing it as a schematic. It simplifies the drawing and makes it easier to run with. All right, before we get to, all right, so we have two different types of circuits. We have an open circuit and a closed circuit. A closed circuit is where you complete the path and the circuit engages. An open circuit is no engagement whatsoever. So it means it has no ability to turn the light on. Yes. And I am recording this so you can watch it on YouTube. All right, resistance. Now this is one of the biggest, there's a trinity that creates all electrical circuits and makes them work right. Resistance is one. Current and voltage are the other two. They are the holy trinity of power. So every electrical pathway has the property of resisting flow. Copper wire offers very little resistance. If you break a wire, it offers more. I will say this, aluminum offers more resistance. That is the bad thing about using aluminum. Yeah. All wire gets hot over time just because of that resistance. If you want resistance, think of what happens whenever you use a space heater. All that is, all those coils of wire, that's resistance. When you run that current through that coil of wire, that resistance causes heat. You break that wire, you're not going to have anything working. It offers much more resistance. We'll talk more about that when we get to Ohm's law. Okay? So the opposite of resistance is a term called conductance. All right? So nothing else, you can think of it as if you've got a river. What do we put on a river to create resistance? You put a dam on a river to create resistance. It's how we create electricity. All right? All right. So here's our river. Here's our dam. Here's the river downstream. All right. We got a nice little lake right in here. That's where all the reservoir water sits. Yes? Everybody knows what I'm talking about. Okay? So your voltage for a river system is what? No, your voltage is up here. This is where you get rain. It's where you have your spring. It's where you have whatever source of water you have. Snow melt, whatever. That river has to have a path to the ocean, right? It's going to get somehow from point A to point B. Yes? That's how the cycle starts again. So we have our rain that comes from the top. The path of it is the river. And then you have, you can have something as small as a rock blocking out part of your passageway there. Does that make sense? So whenever you come to a dam, do we hold back all the water from a river? No. We have spillways. Water will still come over the dam because if you hold back all the water, everything downstream goes dry. On the other side of the dam, you will have water that comes over it. That is your conductance. That is what comes through your resistance. Does that make sense? So the conductance is what spills over the dam, or it's what is allowed through it. Because you cannot actually turn the turbines in a dam without water moving through the dam itself. Does that make sense? So every electrical pathway has the property to conduct. Breaking the wires offer very little conductance. The main thing you kind of need on this page Thank you. Those are the mathematical symbols for these particular sets, guys. Resistances are voltage is V or E, depending upon whether you're talking about somebody that's military or it's a book. Kind of depends on which one's which. Current is I and conductance is G. Now there's a reason I point out that conductance is G, and that's because of this line right here, where it says G is equal to the inverse of resistance, and resistance is equal to the inverse of conductance. In other words, if we go back to the dam analogy, conductance is how much water is let through the dam. Resistance is how much water is kept back by the dam. Does that make sense? And that is a formula you definitely want because we will be using it. You might want to write that particular formula down. We won't use it as much now as we will in DC, but it is one you want to become familiar with. Okay? All right, so let's talk about batteries. I hate to use the word battery because it's not quite right. Here. And I'm going to show you why. So a cell. There is a difference between what we call a battery and what we call a cell. A cell is what a battery is made of because it is a connection of two or more cells. What I have in my hand right now is a pair of 9-volt batteries that I took the casing off of. I did this because it allows you to see the individual cells that make up the battery itself. I am going to pass these around so you can kind of see them. Kind of a neat little show and tell I've created. So a battery is a connection of two or more cells. Each of those particular cells in those 9 volts is a volt and a half. Okay? Your basic A through D cells are generally a volt and a half. Okay? So that's why they're called a cell. They're not generally supposed to be called a battery. A battery is whenever you get two or more of those cells together. This is a created battery. Why? Because it connects 3 cells together. Yes, I keep a flashlight in my bag. It's because whenever I've got to climb under something and look at something, or I've got something I've dropped or something, it's good to have a flashlight. It's not a cell phone. All right, so potential difference. All right, we're talking about potential energy. I will go ahead and tell you this, potential difference is always done in absolute value. Anybody remember absolute value? What does absolute value mean mathematically? Anybody remember? It means that the answer is neither positive nor negative, it just is. Simplify that out for me real quick.
So if you open the battery, they have one of these two.
Now, let me clarify that real quick. If you open that D cell, all you're going to find is wet, nasty, white paste. It's an electrolytic material that is what allows current to flow. Those are strictly 9-volt batteries I was able to pop the cases off of. So that is the reason I'm clarifying that real quick, because if you open a regular battery, all that has is that really, I wish I had something with that on me, but I don't. But essentially, have you ever opened a battery case and found that white, pasty crap that's acidic? Yeah.
It starts to leak out.
Exactly. The white, nasty crud that leaks out into your battery compartment and just burns the crud out of your hands when you're trying to clean it out. That is what is in a typical, what most people call battery. It's actually a cell. These days, most people call it a battery, so everybody calls it a battery. If you open an actual battery, it should have multiple cells like that, but if you open up a cell, it will have that really corrosive white stuff that nobody likes to clean out. Basically, if you ever have the remote that has all that corrosive stuff in it, you're probably going to throw away the remote and just go get a universal one, right? So when it comes to potential difference, this is actually fairly easy to find. You're going to take your positive and subtract on your negative side. This should give you a potential difference of 8. Okay, so again, positive to negative. 2 minus 10 would give you negative 8. Absolute value would give you 8 volts for each of these. It's not something you're going to come across very much unless you use something like one of these. This is a DC voltage power supply. And power supplies are really nice whenever you're having to use testing equipment and extra voltage and things like that. You really are not going to use them a whole lot. But just in case anybody ever needs you to know, the way you find potential energy, you use your positive, subtract your negative, and you get the absolute value is always positive. Okay? Just to kind of get y'all through that real quick. Okay, so let's talk safety. And again, I'll say this, I'm a safety nut. Why? Because electricity is one of those things we don't tend to take very seriously anymore. Okay? We have a lot of toys that base themselves on electricity. Heck, there's one that I've seen that's kind of popular where it's a stick with a bunch of lights in it, and if you grab either side, it lights up using your own bioelectricity. And it makes a really nice little high-pitched sound. It lights up and it goes, nah. That's using your body's electricity. It's a fun toy. Electricity is actually not a toy.
Unit out that brought reoccurring power. Somebody went to mash the button. He didn't say that he was gone. He was gone. That he was finished working on the job, but it was locked out. But what it did, it brought reoccurring power. He wanted to test you. You know.
I mean, it happens all the time. What most people don't understand about electricity, one of the earliest forms of electrical safety they had to put onto houses, does anybody know? To keep houses from burning down. What did they used to have to do? What do they still do? This applies to high rises, this applies to your basic home. How do you ground it? You use a lightning rod and you use a copper metal something to put into the earth. Why? Because otherwise lightning can burn down your house. Electricity is not something to play with. And I'm a nut about this because I know people that have been hurt by it. My dad has seen people killed by it because he was a lineman for years. You know? Heck, there was some guys that were trimming trees and he happened to be nearby. A line went down, and when they're trimming trees around the line, they're supposed to cut power to these sections. I'm going to go ahead and preface it by saying that. They did not cut the power to this particular set of line. And when the tree came down on the line, it brought the line loose, like happens. And these guys weren't aware of it. And they were going to walk up to it. Luckily, he was there. And he told them, don't you go near it. And he saved their lives. Electricity kills. It does it every day, every year. It does not care. Okay? At the very least, if you don't pay attention, it can burn you. At the very worst, it does not forgive very well. the best way you can get forgiveness in it is making sure that the path it takes damages the least amount of your organs. Okay? You're not supposed to work with both hands, you're supposed to work one-handed. Why? Because if you work with both hands, what path is that? Goes right through that, right? And it isn't just your heart that'll it'll take out, it'll take out your lungs. It can paralyze your lungs. You know, it's serious. One of the things you're not supposed to do whenever you're working with electricity is, what are you supposed to make sure you take off? All your jewelry.
Feels better when you're sweating too.
You're supposed to take off all your jewelry. Why? Because most jewelry conducts. These days, they've got jewelry that is made electrically safe. For those of y'all that want to wear your wedding ring, or you want to have something you want to wear like that, they make them out of rubber or they make them out of plastic so that they cannot conduct. Huh? Silicone. Now, there is one problem with that, and that's when it becomes a mechanical hazard. You don't want to know what happens to a person's finger if a ring gets caught. All of a sudden, you're doing a different kind of hello. Put it that way. Put it the nicest way I can. You're not going to be doing hello as a high five. You're going to be doing hello as a 4 high. I'm not trying to be funny, guys. It really is something of concern. Simply because, I'll tell you now, we won't be working with any really high voltages. We have a couple of classes where you do work with higher voltages, and at those points, you definitely want to make sure you don't wear your jewelry to class. But I always try and treat it like you would in the real world, okay? Get into the good habits now and don't wait till later to develop them, okay? All right. So if y'all got any questions for me? All right, so we'll leave it on that, as safety is a big thing. Like I said, it's not something everybody takes seriously, but it is something you need to consider. Biggest thing is, if you ever see somebody being unsafe at work, you might just save their life by going, hey, 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 no, 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 mm-mm. One of the biggest things is, what do we do as one of the biggest things for safety? There is a term for it. LOTO. Lock out, tag out. Okay? And just because somebody did mention it, and there's a reason why I'm going to talk about it. Because the biggest way you're supposed to lock out, tag out is to what? Not just lock it out. Make sure you test. Always go back and test your circuit. I don't care if you just locked it out. Because I'm going to go ahead and borrow an example from Rich Raymond.
Oh, oh yeah.
Yep. Well, I'm going to borrow an example from Rich Raymond, and this is because he brought this example up a few times whenever I was taking these classes, and it's a very interesting story, as well as a very sobering one. He was working down at US Steel, and they were working on, I think, some sort of a roller system. And they had locked out, tagged out, but they did not go back and what? You did not go back and test it. What they did not know was that there was a separate control panel. And a guy had gotten into the rollers. You see where this is going. Some employee that did not know that The guy was crushed to death. Lockout, tag out. Lockout, tag out's the big thing, guys, but the bigger thing behind it is make sure it's not on. Make sure you de-energize. Why? Because just because you are sure that this one system is the one that controls it, there could always be a secondary control system, or a third one, or a fourth one. Housing, if you are working in a house, exactly. I can give you a better example for your housing. For some reason, this is because my house is wired like I have never seen somebody wire a house like this. The worst example of it was my niece's room was right over the garage. We have a nice big pond that we use a pump to run the pond. One day I come home, the pump's not running. Can't figure out why. Okay? Because we never had an issue with it. We always kind of assumed, upstairs is where, for some reason, they have a light switch that turns the pump on or off. But surely it's a dedicated circuit to the pump that runs the pond. That keeps life support for the fish. No. It's attached to the plugs that are upstairs. What we didn't know was the nightlight that was upstairs had burned out and had almost started a fire upstairs. The plug, the nightlight, they were melted. We weren't aware. The only reason we knew anything was wrong was because the pump wasn't running. But let me ask you this, why is an outside pump attached to inside plugs in the house? I'll go ahead and tell you now, I live out past Tannehill where there are no real inspections or regulations. It's not the first time I've found stupid crap like that. That's fine. We're about to wrap up. I will say this, guys. Be very careful when it comes to electricity and respect it, because it can take you out before you even realize. So, yep. Residential wiring should run 120 unless you're working on major appliances, that's 240. And I will go ahead and say this, guys, before I forget, you need to make sure you've got your lab one, the take-home lab. That needs to be turned into me, guys. I should have had it done by now. No, I'm talking about the one that he's got in his hand right there. Yes. Yes, that needs to be turned in. If you have not got it done now, you can turn it in on Thursday at the latest, guys. I want it Thursday. It needs to be done. Huh? Let me get roll real quick, and then y'all are good to go for the night. Yep.
On the mom's side,